Hello, my name is Emily, and I'm going to present to you how to find the structure for the given molecule of C5H10O2 by using nuclear magnetic resonance spectroscopy and referencing different spectra to find out certain characteristics about the given molecule. So first we're going to find the degree of unsaturation. So the degree of unsaturation will tell us whether or not a double bond is present. So the formula for the degree of unsaturation is referenced on this page. So I have the given formula of degree of unsaturation is equal to C minus H plus N plus 1 divided by 2, where C is equal to the number of carbon atoms, H is equal to the number of hydrogen atoms, and N is equal to the number of nitrogen atoms. So for this formula, we have C is equal to 5, H is equal to 10, and N is equal to 0. So if we plug all of that into the given formula up top, we would get 5 plus 1 minus 10 over 2, which is equal to 1. And then down here, I just indicated that that would mean that a double bond is present. Here we have an IR table demonstrating different peaks. This table correlates specific functional groups with their specific infrared absorption frequencies. By looking at an infrared spectroscopy absorption table, we can reference the first chart to figure out which functional groups go with each frequency and peak. So we're going to turn this around and we're going to reference this chart right here. So first, we can find that the first peak is somewhere in between 3,000 and 3,100 centimeters to the -1. So this, by looking at the reference table, we can see that this is a C-H bond. And then the second peak, which is going to be right here, is somewhere around 1720 centimeters to the -1. So we can indicate that this is where C is double bonded to O, which would indicate that a ketone is present. And then lastly, we have our last stretch, which is at around 1250 centimeters to the -1, and this would indicate that C is bonded to O. And then all of this is referenced on the previous page here. So I did indicate the frequencies, which are all listed here, and then the functional groups, which are listed here. So all three carbons, or all of the carbons in the molecule, are going to be sp3 hybridized. Next, we have our 13C NMR chart, which helps to identify carbon environments in a molecule based on the position of the peak on the chart. So the position is measured in parts per million, and we're actually going to reference this second chart here. So right here you can see that each peak is measured in parts per million, or ppm. You can fill in this table referencing the spectra, and by looking at the table with a certain table with chemical shifts in the C13 NMR spectra. So given the different peaks, we see a chemical shift around first 20, and by referencing the chart, we know that the type of bonding environment for a chemical shift of 20 parts per million would be a CH3 group. Next, we have around 37 parts per million. We have a chemical shift, which would indicate a bonding environment of a CH group. Next, we have a chemical shift of around 55, because that's where this peak is right here. And this would indicate an O bonded to a CH3 group. And then last but not least, we have a peak at around 180 parts per million. And this would indicate that C is double bonded to O group. And then on the previous page, I have all of these values filled in right here. In the last table, we're going to look at chemical shifts and other characteristics of protons in the molecule. So the last table is going to reference this chart up here. So first and foremost, I labeled that this side of the chart where the parts per million are a little bit higher is considered downfield, and this part of the chart is considered upfield. The molecules that are, or the value of the chemical shift would depend on the position of the protons. So the protons lying close to the electronegative group will have more chemical shift. So the protons that are over here will have more chemical shift. So in reference of this table over here, we can see that a chemical shift value of right around here is 1.1 parts per million, and the integration number, which I have here labeled as 6, we would get from this 6H up here. The multiplicity we can see is a doublet because there's 2 lines. And then the interpretation would be that the protons lie away from the electronegative group. Next, we have a chemical shift of 2.7, which is a pentet right around here. And you can tell that this is a pentet given by the number of lines. We know that the integration is 1, given this 1H right up here. And then the interpretation for that would be that the protons are close to the electronegative group. And then lastly, we have a chemical shift of 3.7, and we have an integration of about 3, because you can see this 3H right here. And there's only one line, so I labeled this one as a singlet. And the interpretation here is that the protons are next to the electronegative group, because as we stated, the protons that lie close to the electronegative group have more chemical shift. Given all of that information, I came up with the following structure here. Based off of the type of bonding environments that we found from our previous investigation, we have a C is bonded to O group right here. A O is bonded to a CH3 group right here. We have a CH group right here, which is bonded to 2 CH3 groups here. And earlier I did say that all of the carbons would be sp3 hybridized, so that's where these CHs are all coming from. So this would be the final structure and interpretation. Thank you.